So bonds are forces that hold groups of atoms together and make them function as a unit. There's a couple different types of bonds that we've learned about. An ionic bond, which is a transfer of electrons between a metal and a nonmetal, and a covalent bond, which is a sharing of electrons between two nonmetals. An ionic bond, remember, makes a formula unit. That's the lowest whole number ratio between the metals and the nonmetals in the ionic compound. A covalent bond makes a molecule. Now, you've probably heard that term before, a molecule, but in chemistry, we only refer to something as a molecule if it's a nonmetal sharing an electron with another nonmetal to bond them together. So if we break this word covalent down, the prefix co means together, and valent comes from the Latin word valere, which means strong. So two electrons shared together have the strength to hold two atoms together in a bond. So together, they're strong. So many elements found in nature are found in the form of molecules. So a molecule is just a neutral group of atoms that's joined together by a covalent bond. And an example of this would be oxygen. So the oxygen that's in the air you breathe is not just oxygen atoms, it's actually oxygen molecules, O2. It's an oxygen atom bonded to another oxygen atom. So we can see this if we draw it structurally like this, and we'll get into how to do this later in this chapter. You can see there's actually two bonds, so that's 4 electrons being shared between these two oxygen atoms to hold them together as a molecule. So here's how molecules form. Let's look at this example in another diatomic element, hydrogen. So hydrogen is always in the form of H2. So each hydrogen atom has one proton in its nucleus. And those nuclei repel each other since they both have a positive charge. Remember, like charges repel, opposite charges attract. So as these two nuclei, these atoms, get closer together, they're going to push apart because like charges repel. But they're gonna share electrons because they're attracted to each other's electrons. So when they share electrons, this is called a covalent bond. Remember, this only involves nonmetals like hydrogen and oxygen. So as they get close together this time, now each atom is attracted to each other's electrons. So this electron belonged to this atom, but it might spend some time over here. And this electron really belonged to this atom, but it might spend some time over here. And they're going to end up going back and forth between these two atoms. And it's that strength of attraction between the positive protons in the nucleus and the negative electrons, floating around the two is what's going to provide the force, the strength to hold these atoms close together. So like you said, like you've seen here, the nuclei are attracted to the electrons, and they share the electrons, and this is what we call the covalent bond. And again, this only involves nonmetals. So nonmetals hold on to their valence electrons pretty strong. They have a lot of protons. They're further to the right on the periodic table, so they have a strong electronegativity. They can't give away electrons to a bond because they're holding on to them. They have that strong electronegativity, but they still want that noble gas configuration. And they get this by sharing valence electrons with each other. And that sharing, again, when you think of sharing electrons, you need to think covalent bond. So by sharing these electrons, both atoms get to count the electrons towards their noble gas configuration. Let me show you an example with another diatomic element, fluorine. So fluorine has 7 valence electrons, but it would like to have 8, be stable like a noble gas. So fluorine is F, and it has 1, 2, 3, 4, 5, 6, 7 valence electrons, and another atom of fluorine also has 7. I'm going to draw it in yellow to show you the different electrons and where they're coming from. So here's the other fluorine, 1, 2, 3, 4, 5, 6, 7. So neither of them is happy. Their octets aren't filled, but they're almost filled. If these two atoms got close to each other, they're going to start a bit of a tug of war. But they're equally matched. They're both fluorine, so they have identical electronegativities. So in the tug of war for electrons, neither one is going to win. But if they get close enough, they're going to share. And when they share, both atoms end up with a full octet, full 8 electrons in their outer orbitals. And this gives them that noble gas configuration. So let me show you here. Here's this fluorine, it has its original 7 yellow ones, but it's also sometimes sharing one of fluorine's on the left's white electron. So it can still count it in its octet. So it has 8, it's happy. The other fluorine on the left has its original 7 white electrons, but it can share one of the other fluorine's yellow electrons. It also is going to have 8, which is a stable outer shell, just like a noble gas. Here's an animation showing this. Now this goes pretty quick, so I'm going to let it run several times, but you can see we have 2 separate hydrogen atoms, and as they get close enough, the electrons will go back and forth between each hydrogen atom's nuclei, and when that happens, we have the covalent bond being formed on the top, going from 2 separate hydrogen atoms to one hydrogen molecule, H2. So compounds that are bonded covalently, like water or carbon dioxide or any of the other examples you've seen so far, are called molecular compounds. Molecular compounds tend to have some of the same properties due to the type of bonding they have. So they have relatively lower melting and boiling points than ionic compounds. Remember, ionic compounds are being held together with those really strong forces of attraction between the cations and the anions. And because of that, they melted and they boiled at really, really high temperatures. Molecular compounds aren't that strong. The force of the covalent bond is not like an ionic bond. So they have lower melting points and boiling points. So they tend to be gases and liquids at room temperature. So when you think of molecular compounds, have a couple examples up your sleeve. So think of water. Water is a liquid at room temperature. Think of carbon dioxide. Carbon dioxide obviously is a gas at room temperature, which means that it boiled well before room temperature, which is 20 degrees Celsius. Same with water. It melted at 0 degrees, well before we get to 20 degrees Celsius. It's melted into a liquid. So a molecular compound also has a molecular formula. A molecular formula shows how many atoms of each element a molecule contains. It's not like a formula unit, which we talked about when we talked about salts. So table salt, for example, the formula unit was NaCl. It doesn't mean there was one sodium and one chlorine. It was a ratio. It was the lowest whole number ratio in the atoms compared to each other. But a molecule has a molecular formula, which is kind of like a recipe. It shows exactly how many atoms of each element a molecule has. So here's an example of water, H2O. The subscript 2 next to the H tells us that there are exactly 2 hydrogen atoms. The fact that there's no number here next to the O tells us that there's only one oxygen atom. If there is an oxygen atom, it wouldn't make sense to write a little 1 next to it. Otherwise, we wouldn't have written the symbol O. So the formula for water is H2O. It can never be H3O or H2O2. It wouldn't be water anymore. It would be a completely different molecule with different properties. So besides the fact that this tells us the recipe, it doesn't tell us any information about the structure. For that, you might need something like a different type of formula, a structural formula. So there's lots of different types of formulas. So we've seen the molecular formula like this, H2O. You could add a state of matter symbol like gas, tell you that this is water vapor and not liquid water or solid ice. But if you wanted to see the structure of this, you would have to draw a structural formula. And I'll show you how to do this in the next couple of videos. But this is the structural formula for water. You can see it still tells us that there's 2 hydrogens and 1 oxygen. It tells us the number of bonds. It tells us the angle of bonds and the unpaired electrons, which is a little more information than a molecular formula. It doesn't tell us how this thing looks in 3 dimensions, though. This is good for 2 dimensions, writing the formula on a piece of paper. This is good enough. But in 3 dimensions, you might want something more like a ball and stick model like this. Harder to draw for the average person, but not impossible. But unfortunately, this isn't quite accurate. Bonds don't really look like sticks in between these spheres here. So this would give us a decent representation of this molecule, but it's not perfect. If you wanted to see a little 3 dimensions on paper, you can do something called a perspective drawing. So the little dashed lines here on the bond with this hydrogen tell us that this is going in this direction into the paper, and the little triangle on this bond here tells us that it's kind of popping out at the paper. kind of hard to draw. You probably wouldn't be expected to draw a perspective drawing in a Regents chemistry course, but it's nice to know that this is a possibility for you. A little more accurate representation might be something like this. This is a space filling model. Like I said, the bonds aren't little sticks that connect these spheres. The bonds are just kind of these attractions between the atoms and their electrons, the nuclei and their electrons. But this might be how this molecule might look more in real life. So let's wrap up here. Covalent bonds are formed when electrons are shared between two nonmetal atoms, not to be confused with an ionic bond, which is a transfer of electrons between a metal and a nonmetal. So when you think ionic, think transfer. When you think covalent, think share. We're sharing electrons, and it's always between nonmetals, things on the right-hand side of the periodic table. When electrons are shared, each atom can count them in their octet and make stable, happy uh, outer shells, which will result in stable molecules. Covalent bonds result in the formation of what we call a molecule. Anytime you have sharing of electrons between nonmetals, you make a molecule. And we can write a molecular formula which shows us how many of each atom there is in a molecule. We saw that that tells us some information, but not everything. In the next video, I'm going to show you how to take this information and draw a structural diagram, which is going to become a lot more important later on in this course. I hope this makes sense to you, and if you have any questions, please let me know.